eller ulemper for deg å behandle denne? Eller er det basert på det? Det er bra. Her? Er det på den eller? Det er ikke sammen. Vi kan heller bare gi beskjed vinkelisten er bra, så vi kan veldig bra lyder for deg. Er vi i gang?
Okay, so I would like to welcome you to this event, which is a cooperation between the Norwegian Computer Association, the norske dataforening, Tekna Big Data, and also IEEE, the CIS community. Together today we have a workshop with Vegard Flodvig from Oxford. I'll just say some practical information. Emergency exits are that way, straight to the end, and also straight to the left outside this door. So welcome. We try to arrange this kind of network events where it's open for everyone to come, which is interested, and we appreciate you all coming today. Inge will tell you some practical information.
It's nice to see that we are packed in here. There's also some people watching on the streaming, and so some practical information. This recording will probably be available afterwards if we get everything technical to work. And for the people who are watching streaming, you can also give questions. Today we do it, Vegard gives a presentation. At the very end, there will be questions for you who are here at this venue. You can just raise your own hands and ask. If you're watching the streaming at ikt.tekna.no, then there is a comment section below. You can write your questions there, and I will read them out loud here to Vegard, so he can answer them here, and so that way everyone can get to ask whatever they wonder. So I think that's just about that for the practical stuff. It's nice to see you all, and then we'll pass the word on to Vegard Flodvig. Actually a bit, and you can present yourself.
Thanks. Sound is all right? First of all, I just want to thank the organizers for inviting me here to this workshop. And it's really inspiring to see that so many of you have showed up after work, spent a few hours here to learn more about AI and machine learning. So first, about myself. So I work as a lead data scientist in Oxford, which is a software company with offices in Molde, here in Ålesund, and also an office in Gdansk in Poland. So the main focus of today's talk is on AI and machine learning. But in doing this, I also want to go beyond all the hype and buzzwords and really show what this technology is really all about and how we can apply it for business relevant cases. So in doing this, I'll first give more of a general introduction to what AI and machine learning is, and then focus on how to go from a technology perspective to what brings business value. And I will spend most of my time focusing on practical applications and show use case examples of how this technology can bring value. And I'll then end by introducing the more practical hands-on part, which we will work on later today. So when we talk about AI and machine learning, there's no doubt that there's a lot of hype and attention around these technologies in the media. And of course, to have a lot of interest and attention around what we work on is a good thing, but still some of the attention in the media can be attributed more to hype than to reality around these technologies. So that's why the reason it's so important to go beyond that and focus on the practical applications to show how this can be useful. I'll start with this. This is a part from a McKinsey Insight report where they interviewed a lot of business leaders about AI and all these new technologies. And there's a lot of money invested in these technologies. And this is mainly driven by the tech giants such as Google, Facebook, Amazon, and so on. But of course, the reason why they're doing this is because there's big financial interests. And there's a fierce race to become world leader in a very expanding and growing market. But also as part of this study, McKinsey interviewed a lot of business leaders about how they're trying to work and implement AI in their business. And what they see is that there's a lot of interest in these technologies, but still many are very unsure how should they start and how could this be relevant for their business. And that's also something I can experience myself when I'm out talking to various businesses, that there's a lot of interest and attention, but many people are still very unsure why this is relevant for them. And that's important for us working with these technologies to go more into. And some of you have perhaps seen this figure before, which is Gartner's hype cycle for emerging technologies. So much of what we work with when it comes to AI, machine learning, deep learning, all these buzzwords, we see that they're located quite close to this peak here of inflated expectations. And this, of course, has both its pros and cons. And on a positive note, there's a lot of tension around the things we're working on. But in some cases, there can also be a bit of a mismatch between expectations and reality to what these technologies can really offer. So the challenge for us working with this is to take the technology from this peak of expectations and bring it to something that actually brings business value. But when we talk about AI, this is not something that's very new. This has been a research goal since the early 50s. And one of the pioneers in this field, Alan Turing, he proposed a game which he called the imitation game. And there he contemplated about a communication channel between a man and a machine. So if you talk to a machine, if you're not able to distinguish between what's a man and a machine on the other side, can you then say that this machine has some sort of intelligence? And this was sort of the first times when they started to mention what's called artificial intelligence. But we'll not go into the more philosophical details on what intelligence is and is not. But when it comes to machine learning, this is also not anything new, and it has been known for quite some time. But having access to the vast amount of data and the powerful computing resources we have today has really driven progress in this field during the last few years. And also when we come to deep learning, there's been a huge breakthrough in the last few years. In 2012 with the ImageNet contest about identifying objects and information from images. And we now start to see deep learning models that has performance at the level or even better than human experts. And of course this opened up for a wide range of interesting applications. So So why have we had this sudden hype around AI and machine learning? Since this is technologies that also existed about 50 years ago. And there are some key factors that explain why this has become so big in recent years. And one thing is, of course, the amount of available data, which has been growing in an exponential pace. And this is both in terms of the number of devices, but also, importantly, the connectivity between all these devices through the Internet of Things. And of course, this enables the transfer and flow of information and data between all these connected devices. But having access to data, that's one thing, but you also need access to cheap and powerful computing resources to actually process these data. And this is where the advancement in computing power the last few years have been really tremendous. So as a comparison, if we go back about 15 years, we have a picture here on the left from inside the NEC Earth simulator, which was the world's fastest supercomputer at that time. Whereas now you can buy a quite ordinary graphics card, you can put in your ordinary workstation in your office, and you essentially have access to the same amount of computing power as a state-of-the-art supercomputing facility only 15 years ago. And this, of course, makes a big difference for all of us working with machine learning. So, to summarize, although machine learning is not a new technology, there are these complementing factors of having access to huge amounts of data and cheap computing power, and also that the research done by tech giants like Google and Facebook, they share their research openly, they open source their tools, which makes getting into this field a lot easier than what it was just a few years ago. So if we add up all these different factors, this can explain why we see this sudden hype around AI and machine learning in these last few years. And so machine learning, that's one of the main technologies enabling progress within AI, and one of the areas where there's most investment. But I'll not go very much into the technical details quite yet, but machine learning is essentially about extracting useful information from data. Where data in this context could be anything from text files, sensor data, images, video, sound, you name it. So next, as an example, let's say we train a machine learning model to predict housing prices based on previous sales and relevant data from the properties. Having this, we can then start to make predictions on the values of future sales based on this model. And this is also an important point I would like to mention. And this is the typical distribution of work effort in a machine learning project. As you can see from this visualization here, in many cases as much as up to 80% of the time is spent on collecting and cleaning your data before you can actually start to do some machine learning on that. So what this means is that in a typical short time frame, let's say 12-week proof of concept project, you might spend your first 9 to 10 weeks just collecting and cleaning and processing data before you can actually start to build machine learning applications. And this, of course, highlights the importance of having a good data platform in place to make sure that you have your data easily available in a consistent format to speed up this initial data harvesting and processing phase. And in my experience, this is definitely an area where there's a large potential for improvement as well. But of course, data science, machine learning, AI, that's one thing. But in order to actually build good products, you need more of a cross-functional teams and competency. So on the one hand, you need something with the domain knowledge about the problem you're actually trying to solve. So how is the data captured? What are the possibilities and limitations within the system? And how can this solution actually be applied in practice? And then you have the data science component, which involves things like signal processing, machine learning, AI. which is essentially about finding and explaining patterns in your data. But then you also need the key component around the software engineering. And this is crucial to build good data-driven products and solutions. So how you harvest and process your data through proper pipelines, ensuring that you have access to data, proper security measures, creating good tools for end users. That's all very important ingredients to build good products. So you essentially need to combine all these different ingredients if you want to build good products that can actually bring you some value. And so if you want to go from sort of hype to applications, how could you evaluate whether machine learning is actually a useful tool in your projects? And it's important to keep in mind that machine learning is not a magic black box that could solve any problem. So the first thing is to actually find the right tool to solve the problem at hand. And you should always also focus on what could bring value to your business. Start from the business side, identify the right cases, make sure you have a clear goal and purpose of the analysis before you jump straight into the technical parts. And the key ingredients to building a successful machine learning project is not about who can implement the latest, most advanced algorithm, but it's having access to the right data. And in doing this, you need first to collect data that contains the information you need in order to solve your problem. And this is a phase where having someone with the right domain knowledge is really crucial. And you also need to specify what's the end product of this. Are you building a new product? Are you improving an existing process? And in doing this, you need to adapt the method to the desired output of your project. So the main reason for companies investing in new technology is that it should provide them with some real value. Not because it's nice to have or everyone else is doing AI. The marketing department said that we need to do something with AI. So this was sort of a very brief introduction to the machine learning and background on that part. But now I want to focus more on the actual applications. So going through a few use case examples of how machine learning and AI can be used to bring real value for business in quite different areas. So this ranges from using data analysis and machine learning for condition monitoring of say heavy-duty industrial equipment, motors, compressors, to computer vision applications, object detection, and things like that. So this first case is for a typical production company. And this could be the fabrication of some kind of complex equipment or a processing plant, or in general just anything where some kind of produced unit is the end product. So in a simplified view, what we're trying to do here is to use all the available information we have from various kinds of sensor data, like temperature sensors, flow sensors, pressure measurements, and then find any relationship between all these measured variables and the quality of the produced unit. So let's say you have a failure rate of your products of 2%. So 2% of all your produced units are simply discarded. And this, of course, has a huge cost for the production company. So if you can find any patterns in your process data that can explain this and improve the quality of the product, this could save you a lot of money. So the idea of a machine learning model here is to use historical production data and then find any relevant relationships between the process conditions and the quality of the produced unit. And if you can find this pattern, then you could investigate and couple the machine learning model to the current process condition in your plant, and then give a prediction on what's the risk of having a discarded product. So this could also pinpoint you into which parts of the process you should focus on to optimize in order to improve your production quality. So this is another case also for a production plant regarding production optimization. So this could be any kind of production plant where you want to increase your efficiency when it comes to energy optimization, production volume, number of produced units, or whatever. So in a typical processing plant, there's a lot of variables you can adjust in order to control your process. This, of course, when you have very many variables to adjust, this is a difficult problem to solve. And in many cases, this has historically been solved by the experience of the operators. So after working with this for a few months or years, they obtain sort of a gut feeling what's the correct way to run their process. But this is a problem which is well suited for machine learning. So analyzing high-dimensional data, finding subtle patterns which you can then use to optimize performance. So this then can give you, this can be run through an optimization model, which then gives you advisory input on how you should run your process in order to maximize performance. And as an initial step, this could be seen as sort of advisory tools for operators, suggesting how they should run the process. But in the long run, this will more probably lead to more autonomous operation of process plants. So this is a different example covering condition monitoring of, in this case, a compressor. So in this case, we're also monitoring all these sensor values, like temperatures, pressures, vibrations, and so on, and simply look for signs of anomalies. So the idea here is that the machine learning model learns through experience. So it gets a feeling of what's the normal behavior for this piece of equipment. And then if you start to see deviation from this, then this should trigger some kind of alarm or a warning of an upcoming failure of the equipment. And of course, having early warning of upcoming failures, like we see here, is extremely useful information to have if you have this piece of equipment. So this means you could avoid sudden breakdowns of your equipment, which allows for controlled shutdown of critical pieces of equipment. So this is both an interesting and very useful industrial applications of machine learning. So to extract information hidden in large quantities of, in many cases, very messy, high-dimensional sensor data. So moving a bit away from industrial cases to sales and logistics forecasting. And so for the case here, we have data from a chain store with available sales data from the past 5 years. So the idea behind machine learning in this case is to analyze these historical sales data and see if there's any subtle patterns they could use in order to forecast the future sales from each store. And as a test case, we then use these 5 years of sales data, and we wanted to build a model that could forecast the sales for the last quarter of 2017. So the results here is that just using historical sales record, you could build a machine learning model that could predict sales within an accuracy of about 3% compared to the real sales during this last quarter. Of course, this has some useful applications if you run a chain of these department stores, where you can, in a much better way, plan your logistics, distribution of goods, warehouse optimization, all these kind of things. So now we're moving into what is called as sort of deep learning. So we're now all the way at the top of the hype cycle you saw earlier. But deep learning is not only hype, but it also has some really interesting and important applications. And it's important to keep in mind that this technology is not magic. It's based on mathematical models where images seen by the computer is simply just a bunch of numbers. And you can then wonder, why do we call this neural networks? What does this have to do with our brain or neural networks in general? And it actually has some quite interesting connections to how our brain works to process information. And previously I was working as a period as a researcher in computational neuroscience, trying to understand how our brain processes information and analyze what we see. And there's a really quite striking connection between the neural network in the visual cortex in the back of our heads and how these deep learning models work to actually analyze images. So the reason why this is called deep learning is because these models consist of a series of layers which analyze different kinds of visual information. And this is the same as in the visual cortex. When we see something, this information is brought from our eyes back to the visual cortex in the back of our heads, and then analyzed through a series of neural layers looking for different kinds of information. So in the first few layers, we typically look for rough shapes, light conditions, shadows, angles, as shown here. And then these sort of simple basic pieces of information is brought to the next layers, where we gradually build up more and more complex structures, which in the end start to resemble more closely the object we're actually looking for in the image. And this is of course something we need to learn a computer. So how do you learn a computer what's the difference between a car and a bus, or a cat and a dog? So we don't give the computers instructions how things look like, but they learn through experience. And this is essentially the same way human learns as well. So for those of you who have kids, you can probably relate to this. So let's say you want to teach your kids what's the difference between a cat and a dog. You don't give them a set of instructions that the cat is this big and it has this height, but rather you show that every time you pass a dog or a cat, you say, okay, that's a dog, or that's a cat. And if you do this, what seems like an infinite number of times, the child eventually learns to distinguish these objects. And this is essentially what we do with these neural network models as well. So we just give them example images, it makes a random guess, and each time it makes a mistake, we tell it, okay, you did a mistake, try again. And this is done through mathematical models of how the brain works. And then after looking at a few hundred thousands or millions of images, these models start to learn what distinguishes different kinds of objects. And this is why we now see performance going beyond human level. So this means that deep learning models are actually better than humans in analyzing images and seeing what kind of objects you see in the image. And this opens for many very interesting applications. And one sort of more fun side project is that you can learn this model to paint. In this case, in the style of Edvard Munch, a famous Norwegian painter. So what this model does is that it takes as input this image from Edvard Munch, the screen, and then it tries to analyze what is the characteristic features of the painting style of this artist. And when it has learned what are the sort of main features, you can then give it a new image as input, and then try to use this as inspiration to create a new picture in the same style as the original painting. And this thing about AI-generated art and music is actually becoming a reality, and it is displayed in galleries all over the world. And what's interesting here is that when we talk about art and music, this is typically a thing we strongly couple to sort of human-like intelligence and creativity. So it's interesting to see that machines can actually perform this well also in these very human-like domains. And producing art like this is probably not the most useful applications, but what is important is the underlying technology here. So how these models can extract information from images and then use this to give us predictions. And one very interesting example here is when it comes to medical applications and use of these technologies in healthcare. So for the example here, I used same kind of models to look at chest X-ray images. So this is one of the common techniques to diagnose pneumonia in patients. But of course, in doing this, you need access to expert radiologists in order to look at these images and determine if the person is healthy or not. And that's a very interesting opportunity to use these technologies to automatically classify these images in order to save time for the human experts. So currently it's not about replacing the human experts, but it's using this as a support tool for them to save time and improve diagnosis accuracy. So the example here is just the results from a small test case done in about afternoon. And just based on a few thousand images openly available online, you can, with relatively little effort, train a model which performs as well or even better than human experts in detecting pneumonia in these kind of X-ray images. And when it comes to AI for medical applications, this is going to be a huge market in the coming years. So, and it's also a very interesting application of AI from a more technical point of view. So here we have an example where this technology has been applied to a more industrial type of case within quality assurance. So scanning images, looking for certain kinds of defined characteristics such as corrosion, damages, cracks, bad welds, and so on. So this is actually showing some images of a project we did for a company called Access in Molde. And as a rule of thumb, any object in an image we humans can identify, we can also train a machine learning model to do. But of course, in order to do this, you need access to labeled images to train up this machine learning model. And for more simple basic applications, you might need tens or a few hundreds of these images, but for more complex, more advanced applications, you might need tens or even hundreds of thousands of images. This is also another example of use of this object detection technologies, in this case for monitoring fish health in fish farms. So this is a really exciting project we worked on with a startup company in Molde called CreateView. So monitoring the health of fish in fish farms is not really a very easy task because the fish is living underwater, so it's not easy to see the fish. So in this new exciting solution, they have deployed underwater cameras in the fish farms which constantly film the fish swimming by the camera and take images each time a fish passes by. And this image is then analyzed by these computer vision models looking for things like lice on the fish, deformities, sick fish, all these kind of defined characteristics. And of course this is good for fish health, since the fish doesn't really like to have lice. That's not a good thing. But it's also good financially for the fish farm owners, because healthy fish means more profitable fish farms. And it's also quite an interesting example of how we can use technology to get more sustainable food production and also increase animal welfare. So in this case, I think it's a really good use of technology for a good cause. So the main takeaway message from my talk so far is that we should go from a technology perspective to what brings business value and focus on applications. So starting from the business side and formulating the right ideas and the right use cases, we should then find the right technologies to solve this problem, and not the other way around, which is becoming a bit too common. So we shouldn't use AI just because everyone else is doing it. We should really do it because that's the right tool to solve the job. And also importantly, to build good products, we need multidisciplinary collaborations. So you don't assemble a small team of data scientists and expect them to solve all the problems. You need domain experts, software engineering skills, and combine all this to build or really to find the good solutions. So I hopefully at least give you a small taste of what machine learning can actually be used for. That is not only a hype, but also has some interesting applications. So the next step now is to move more into the hands-on part, which is the more practical use cases we're going to work our way through all together afterwards. So I'll just start by briefly introducing the tutorials that we'll work our way through. So I prepared 2 different tutorials that cover a bit of different use cases, as there's most likely some difference in interest, what kind of topics you prefer to work on. So you can feel free to pick whichever of those you want, but the first one on image classification is perhaps on a bit more basic level. So if this is the first time you try to build a machine learning model, I would suggest to start with that one and then move on to the next one afterwards. So for the first case, we want to build an image classification model, which is one of the important applications of deep learning. So the task here is actually to extract information from images. And we should keep in mind that images seen from the computer is just a bunch of numbers. So we're going to build models that analyze numbers and then tries to say something about what this image contains. And in doing this, we can distinguish between different kinds of models. So we have image classification on the one hand, as in this first example to the left, which is sort of analyzing what kind of object is contained within the image. And then if we move this to the next level, we now have object detection, which also tries to pinpoint where in the image this object is located. And this case is slightly more complicated when it comes to both the types of models we use and also the amount of pre-processing of the training material. So this is a bit out of scope for this tutorial today. So that's why we'll focus on the image classification case. So you might have heard that deep learning models require massive amounts of data. But in reality, this is not usually what we have. And the solution there is to base our approach on models that has been pre-trained by giants like Google or Facebook, which has been trained on millions of images. And the good thing here is that we can use these models and use the knowledge acquired by these large training sets and then just adapt this to the applications we have in mind. And this is something called transfer learning, which is extremely useful for us working on more practical applications of these technologies. And the reason this works so well is because of this layered structure of these deep learning models. So we said that the deeper layers of the model learn more basic features like rough shapes, shadows, light conditions, and then as we move up in the model, this looks for increasingly complex structures which more closely resemble the kind of objects we want to train our model to look for. And this means that we can take these pre-trained models and use all these sort of deeper, more basic features of the model and then just retrain the last few layers, focusing on the more specific objects for our application. And this is extremely useful because in most practical cases you don't have access to millions of images. Probably you have more like hundreds than millions. So this is the example case we're gonna work our way through afterwards. So we want to classify traffic signs. So the goal here is, given as input one of these images, where I've shown some examples here to the right, we want to build a model that can classify this as one of the categories listed here. So what kind of traffic sign does the model see? And also to make it a bit more realistic, I've limited the amount of training images for the model to be less than 200 for each of the categories. So it means quite low amounts of data. And we also used images of fairly low quality, so low resolution, bad lighting conditions, slightly blurred images, because that's usually what you also would encounter in a real life setting. So, as often is the case, we don't have many images. They're not of very high quality, but there are some tricks we can do to improve this. And one of these strategies is something called image augmentation. So what this essentially is that we take our original set of images and we make a bunch of copies of that images with some slight alterations. So we could do some rotations or cropping out parts of the image. We could change the contrast or lighting conditions. So this is a way of artificially increasing the amount of training data for our model. And this makes the model better at generalizing and makes it less sensitive to small perturbations of our images. And this is often a very useful strategy because in most cases we don't have that much training data. So this slide illustrates sort of what kind of results we can expect when you have completed the tutorial. So in this sense, it's really a good example of the power of transfer learning. So we see that even with quite a limited number of low quality images, we can actually train a model that can classify the correct traffic sign in about 99% of the cases. So a common way of evaluating these kind of classification models is through something called a confusion matrix, shown to the right. So what we essentially do here is that we compare the true label of the image on this axis versus the predicted label from the model. So let's say in the first case of the images of bikes, the model predicted bike in 100% of the cases. So perfect. Whereas for intersection, we see that the model predicted the correct result in 95% of the cases, but in a couple of cases it also predicted pedestrian or a yield sign. So it's not perfect, but close to it. So as you follow along this tutorial, you can feel free to change things in the code. Just simply play around a bit and see how this affects the model performance when you play around and try different set of parameters. So moving on, this is the next slightly more technical tutorial on condition monitoring using sensor data. So the example case here is the test rig shown in the image to the right, where we have a shaft with a fixed rotating speed of 2000 RPM. And then have a radial load here on the top, and a sensor. We have mounted accelerometers on 4 different bearings along this shaft. So in these tests, this equipment is run all the way until failure. So all the way until something breaks down, and then the experiment is stopped. So the idea here is to use the recorded data from these experiments, build machine learning models sort of to monitor the health state of the equipment and see how far in advance can we tell that something is about to happen to this piece of equipment. So this is what we call an anomaly detection model. So you recall from earlier that this model learns sort of what's the normal behavior of this piece of equipment, and when we start to see deviation from this, this is usually a sign that something is about to happen. And of course the goal here is to get early warning of upcoming failures. So the test here is to see how far in advance of the actual failure can the model predict that something's about to happen and give warning well ahead in time to allow for a controlled shutdown or maintenance of this piece of equipment. So this is of course a very useful applications of machine learning for industrial cases. So you see that in this case, we built a model that could give us a heads-up warning about 3 days ahead of the bearing failure of this piece of equipment. So that was it for introducing the tutorials, and now we're getting closer to start on the fun part, which is the hands-on session where you will actually try to build these models yourself. And for many of these, this is perhaps the first time you build a machine learning model. So hopefully the outcome of being here today is that we can demystify some of the things. And so you can see that this has nothing to do with magic. It's just applications of mathematical models that do these kind of tasks for us. But of course, both me and a couple of the organizers will be here to help you out getting started if you get stuck on any problems. So I think now it's time to do a few questions to this first part, and then we'll do an introduction of the Google Colab, which is what we use to share the notebooks we'll work through later. Thank you.
Thank you for your presentation. Very nice. It's obvious that machine learning is good for image recognition. Are there examples where machine learning proved to be not good?
You mean that image recognition or other cases in general?
Other cases, other applications.
I think there's probably an infinite number of examples where machine learning has failed. And also within image recognition, this is these models are not intelligent in the sense of our intelligence when we look at something and analyze what we see. So they can easily be fooled. That's an important failure of these kind of models. So perhaps you've seen these articles about people wearing a special kind of t-shirt to fool image classification models. So once you wear this sort of small patch on your shirt, the model is not able to see that you're a human anymore. But of course, as humans, this seems ridiculous, right? So you can still see that this is clearly a human. But for the machine learning models, this doesn't make sense at all. And there's also been some examples with self-driving cars, where they place small of these adversarial patches in the road, which can actually fool the car into steering in the wrong direction. So it's important to keep in mind that even though, let's say, this can classify images with close to 100% efficiency, they can also be fooled doing things like this. So we still have some way to go before we see bulletproof applications of these technologies.
Thank you.
Yes?
Since machine learning basically works on pattern recognition in data, how does it deal with phenomena that's inherently random, like turbulence, for example?
I actually have seen or read a few papers on trying to use these kind of models to predict chaotic systems, which is close to turbulence. And I think they did quite a decent job at predicting at least some point into the future. But of course, if something is completely random, then there's no information in analyzing previous data, right? So if you want to build a machine learning model to predict a random walk, then that's probably not going to work. So it can give you some indications of, yeah, let's say during the next 100 steps of your model, you will be within this sort of range. But to give an accurate prediction, that would probably not be possible. And that's also interesting when people talk about using machine learning for predicting the movement of stocks, which in some cases have been argued to be completely random processes. So I'm not seeing anyone actually solve this problem yet. So when it comes to predicting random systems or chaotic systems, yeah, perhaps it's not going to work that well. Any questions from the live feed viewers?
No one yet.
So if there's no more questions, then I suggest we take a small 10-minute break before we start. One question? You want to introduce the... Yes, sure. So we want to introduce how you get started with the actual tutorials.
Can I use your computer for a second? Yeah. Can everyone hear me fine, like this? Thank you very much for coming here. It was really interesting to hear what you have been working with and studied. That was cool. Colab, I guess some of you have already opened the URLs here. if I can do that from here as well. So, I'm not sure how many of you are familiar with Python and then Jupyter notebooks. Notebooks are basically, as you can see here, a way of putting text and code in the same environment, and you display it. It's a very nice way of exploring data, showing results, and walking people through tutorials. So that's why we chose to use it. A Jupyter notebook is this environment, but Google has made a free version, which we like here at Sunnmøre. So we can go to, if we go to run, so when you open this link, you will need to go to File and create a copy, because this is our frozen document. You cannot alter it and you cannot run it. So you need to click Save a Copy in Drive, and when you've done that, you will have a local version and you can run it. This all runs in the cloud. It's a free service from Google, so you won't require a hefty GPU like Vegard described. So the next thing you want to do if you want to have a higher performance is to click Runtime and change runtime type. Then you can choose what kind of hardware accelerator. As Vegard mentioned, GPUs are very popular, and because they're more or less required to train deep neural networks. Since this is Google, Google has made their own TPU, tensor processing unit, which are supposed to be even faster for training models. So you can experiment with which one you want to use, but the GPU, as per my experience, is quicker, because I think they have more available GPUs than TPUs. So when you have chosen the GPU, you can run line by line by clicking Shift Enter, or by clicking Run somewhere here. Now it's not shown because this one is frozen. Oh yeah, okay. You can click there, run every cell, go down and see what's going on. I've added some code here which is hidden. You can open it if you want, but you don't need to know what happens there, because it really just downloads a file and unzips it so that you have the data. And here in the left pane you have a folder. You click it and you will see what data is in your directory, what the data that Vega has prepared for you. So I'm one of the helpers, assistants, and Magnus over there and Frank outside. We are trying our best to help you guys.
So if this seems confusing and difficult, we'll walk around and help everyone get started. If you get stuck on how you should start.
And also, if you're wondering then where is the link, you can go on ikt.tekna.no and go click on just below the video window. There's a PDF on the last page. You'll find the two links. That also goes to everyone who's watching the streaming. You can just go into the PDF, click the links, and try on yourself. Of course, not with the help of these people. And finally, I just want to say, before we close the streaming, I just want to say thank you very much for coming here and organizing and presenting this. We have a little sustainable gift card, which is a renewable energy project that you are now supporting, which is cutting the amount of 2,750 kilos of CO2. So you have done something good for the environment as well. Thank you very much.
Thank you. Yeah, thanks Vega for a great talk. It's very interesting. I just want to say some practical information. It's the door